No worries. Thank you very much for the introduction. Thank you very much, organizers, for providing the opportunity to present on our most recent development in the field of parahydrogen-induced instrumentation and hyperpolarization. First off, I would like to disclose my conflict of interest in my relationship with ThOD Technology, the company that commercializes some of the hyperpolarization technologies that you will see today. The motivation for our work is really to develop new hyperpolarized molecular imaging probes and also instrumentation for application in relationship to lung imaging and cancer imaging. And we would like to do these in a cheap, disposable, and small fashion, ideally handheld, again, with the vision to be able to put it in the hands of our clinicians in the future. Before I'm going to start with the scientific part of the presentation, I really would like to emphasize that the work you're going to see today, it's not the results from just our group. It's really a huge collaboration between over 10 different groups all over the world. The names that I'm highlighting here in blue, these are the people who are present here in the audience and the people who we are welcome to talk to. So hyperpolarization using parahydrogen, by definition, has to happen with parahydrogen being as a source of polarization. So this is basically where the story begins. And it doesn't really matter which technology you would choose, either it's hydrogenated FIP or Saber technology, where we use exchange of parahydrogen. We always start with parahydrogen as a source of our polarization. How do we get to that state? Well, we cool hydrogen mixture to a very low temperature, and parahydrogen is a lower spin isomer. So once we shift the equilibrium quickly using the catalyst, which we keep at the cryogenic temperature, and once we extract this parahydrogen gas, we can now use it. So in the practical terms, the way it is accomplished is what is we call parahydrogen generator. So this is an example of one of these devices, and by no means I'm trying to walk you through the design of this device. This is just a photo. With the point here that on the positive side, we can have very high production speeds. We can be producing 4 standard liters per minute. And we believe we can produce what we call 1 clinical dose in approximately 1 to 2 minutes. It has almost no maintenance or consumables, so these are great things. On the other side, we need to remember that this device costs quite a bit of money, so this is not exactly low-cost technology. From that perspective, it requires sighting space, even for this semi-portable device on the wheels. There are certain sighting requirements from the perspective of noise and cooling requirements, so it's not exactly a fun device to have. So some of our collaborators, they're basically like, well, Ed, can you make some of the parahydrogen and send it to us? So one way to do it is to put a dispensing manifold, and here we have 2 tanks, which you see at the bottom. We put the parahydrogen in the tank, and we ship it using FedEx. So in this particular case, we package it at Wayne State University in Detroit, and we ship it to NHLBI in Bethesda, Maryland. In these large tanks, parahydrogen decays rather slowly. So again, you need to remember, one reminder here is parahydrogen has spin 0, so it's NMR invisible. So at the beginning, when we do quantification of parahydrogen, we see almost no signal. And as parahydrogen back converts to orthohydrogen in these tanks, we start seeing more and more signal from orthohydrogen until it fully recovers back to 75%. So again, the chart here shows that parahydrogen decays rather slowly in these tanks, and again, this is one way to do it. It's not exactly a fun way to do it because it costs quite a bit of money, and you're transporting something large, which is, again, not ideally suited for an MRI suite. So the innovation that we've been working on is really trying to package parahydrogen in much smaller cans, which are handheld and can be potentially deployed in a fully disposable fashion, where once you're done using parahydrogen, you can put it in a recycling bin or aluminum container, and the whole cycle starts. You don't have to ship anything back. These are cheap, disposable. So what we do here is we fill parahydrogen in these small cans. We have 2 different sizes, 0.1 and 0.2 liters. And then we eject hydrogen and quantify it several days after, and we do it in a repeatable fashion. And as you see, for the smaller can, we get a TS, or the exponential decay constant of approximately 3 minutes. In case of a larger can, again, here we're blaming wall relaxation and mean-free path. It gets longer. Here we have something on the order of 6 days. I believe when we optimize this container, we can potentially push it to about 3 weeks for TS. So this is a nice way to store parahydrogen, distribute parahydrogen in the future, give it to your clinicians and put it literally in the hands of the clinicians. So now we're switching gears to the applications. As I indicated, one of the applications is lung imaging, and right now the best way to do functional lung imaging, in my view, is using hyperpolarized xenon. Warren recently told me that the price of xenon is skyrocketed, so I'm not sure how we're going to handle that in the future. Meanwhile, if you use hyperpolarized xenon, if you give it as an inhalable contrast agent, you can get these beautiful images or something much better on a single patient breath hold. But there are substantial challenges with hyperpolarized xenon. The hardware is quite expensive. It costs on the order of like $500,000. Xenon is a production of hyperpolarization, has low throughput on the order of like 1 dose per 30 minutes. Potentially can be done faster, but this is kind of the ball game. Xenon is far less sensitive than protons from the perspective of the detection, and clinical MRI scanners like the ones we have in the hospitals, they're not exactly equipped for xenon. So one solution that we envision is to use proton hyperpolarized gases as the means of carrying polarization, giving it to a human subject, and then doing the imaging. So here's the slide from our collaborators, and this is kind of the dream of using diethyl ether as a hyperpolarized agent. Perhaps they're taking it a little bit too far, but that's how they think it can be done. There are several requirements if you want to do it properly. One is the hyperpolarized state must be retained for sufficiently long period of time to be able to produce the dose, give it to a human subject, wait, do the imaging, and then exhale. It must be biologically compatible, should be relatively cheap and fast to produce. So during COVID, we were learning a lot from industry. So this is an example of a non-FDA approved device because it doesn't require FDA approval using aviation grade oxygen. This device is available at your local Walmart. So what's really fun about this device is it has high pressure inside, 10 to 20 atm. And once you pressurize this device, or actually once you press on this device, a stream of gas goes out into a mouthpiece, which directly goes into a mouth of a patient. So to me, it was like mind-blowing. Oh my God, you can do it that simply. So we're borrowing a lot of things from already developed solutions. So here, the agent of our choice is hyperpolarized propane. The way we produce hyperpolarized propane, which you may have already seen at this conference, is using reaction of pairwise parahydrogen addition to unsaturated substrate, in this case propylene. We hydrogenate, break the symmetry of parahydrogen. These two hydrogens are now have distinct chemical shifts. If you do this detection high enough field, you can see one line being polarized up, the other one is down. You can image this gas. So here we're producing hyperpolarized propane stream continuously, and we're performing 3D imaging at 4.7 Tesla continuously. We're getting beautiful images, high 3D resolution. The challenge here is once you stop the gas, the magic is gone because T1 is 1 second. So that's a deal breaker. So luckily, we can use long-lived singlet states or long-lived spin states, whatever we'd like to call them. And here in propane, they're created naturally. In case if you're in the strongly coupled regime, we are able to triple the relaxation constant. And in this case, if you look for the pressure dependence of hyperpolarized propane on the left, you can see that at the clinically relevant condition of 1 atm, we get TS on the order of 3 seconds. So this is kind of the time scale which I believe is potentially suitable to be able to produce it, quickly give it to a subject, take the images. But again, the whole point here, everything has to be done very, very fast. So this is the design of our disposable polarizer. Again, you can learn more from this poster 074. So again, here, instead of charging parahydrogen in one of these mixing cans, we actually put in both parahydrogen and the precursor, and using this can as means to propel the stream of the gas through the heterogeneous reactor that we have here. So the way we initialize this is by using the feature of the storage can, which is a high flow valve. We press on it, gas comes out, goes through the reactor, and we have the release of hyperpolarized gas. This part is optional, and we really have it just to be able to do our phantom studies, to be able to do imaging and spectroscopy. Gas comes out, goes inside of the phantom, and then leaves it through a safety valve. So how does this device perform? It performs quite remarkably well. So what you have on the left is the overall idea for the study. We release the gas, goes through the reactor, and then comes out into our 1.4 Tesla spectrometer. And what we detect here, we are in the weakly coupled regime. We're seeing our protons HA and HB. So we have two hyperpolarized signals. And in this particular study, what we did, we prepared a whole bunch of cans and we released them at different timings, like day 1, day 2, day 3, and so on and so forth. So the most important takeaway message here is parahydrogen stays in the form of parahydrogen even in the mixtures, which I guess is totally expected. And the decay rate of parahydrogen here is approximately 6 days, which is quite remarkable. You can charge these tanks, you can cans really move them whenever you like it and then perform imaging. With respect to how well it performs similarly to our other setups, except that here we have a portable setup. So what you see here, you see a high flow of hyperpolarized propane, 7.5 liters per minute. So when we flow that fast and when we start the detection, we don't see anything. Why? Because the gas leaves very fast the detection region. Once we stop, we see a rise in the signal and then decays due to T1. So what you see on this slide, it's basically like a reproducibility measurement where you press the tank valve several times and you see the signal going up, down, up and down, up and down. And the key message here is that it goes up to exact same level, showing how reproducible this device, how robust it is in the use. It basically works the same way at different pressures, flow rates, and so on and so forth. We reach 100% conversion. So in case if we perfectly mix the two gases, the only gas that leaves is hyperpolarized propane. So this is an example where we basically charge these cans at Wayne State University, move them about 100 miles to the site of the clinical imaging facility, and we run GRE imaging. So here you have a series of slice selective GRE images. And again, on 3 Tesla unmodified MRI scanner, just using straightaway sequences. There are some imaging artifacts here. We know why we have them. And this is a comparable image of water at the same conditions. So the key point here is we can image with very high resolution if we really want to, using clinical hardware. In case if the speed is the name of the game, you can go with API. Again, here we have severe artifacts, but the key takeaway message here is we can acquire 8 slices in 0.6 seconds, so we can effectively complete the entire MRI scan in far less than a second. So that's how we envision a potential future development and future validation in animals that I hope we will be able to do in the next year. And now we're going to switch gears to a different project where we produce liquid hyperpolarized contrast agents using Saber hyperpolarizers or FIB polarizers, whatever you'd like to call them. The whole idea here is to create microtesla magnetic fields and use these microtesla magnetic fields to employ them for hyperpolarization. So what you see in this photo, you see Shiraz, who developed and built this hyperpolarizers. You also see 1, 2, 3 different devices. The 4th is going to be coming quite soon. So we run multiple devices in parallel. Why? Because we can. Why? Because we have more students. So what's inside of this device? We have basically bubbling of parahydrogen, which is dosed very precisely using mass flow controller. We can stop it using this bypass valve. What we have inside, we have magnetic shields, we have the Gaussian mechanism, we have a mechanism to recreate the microtesla magnetic fields inside of this device, either in a static fashion using DC power supply or using all kinds of very fancy waveforms. You've seen some beautiful talks by Shannon Erickson 2 days ago on the use of the waveforms. Once we perform polarization, we pull the sample out and we move it to the benchtop NMR spectrometer for the detection, which is not shown here. So here is the application of this device to hyperpolarization of pyruvate. What we do here is we create this fancy complex, which we call 3B. Pyruvate binds in the equatorial plane. Once we perform hyperpolarization, when we bubble parahydrogen at a matched magnetic field in the microtesla magnetic fields, polarization spontaneously gets transferred to each one of these carbons. We can detect both of these carbons. So here's C1 carbon, which is polarized to 25%. And again, the takeaway message here is we're doing it at natural abundance. So the concentration of C13 here is like 90 micromolar, which is, for me, is quite ecstatic to be able to do it on a benchtop device. We can create artificial spin systems where we basically slow down the exchange so much as we shift the equilibrium to low temperatures, where the exchange is so slow, we only see the bound resonance being hyperpolarized. Why do we want to do that? We want to be able to see how far we can push polarization in this complex. So for us, At this state, we were able to show that we can push polarization to over 39%. So what this means, fundamentally, we can reach very high levels of polarization for pyruvate. Why is that become possible? Well, the rates of the spin destruction, which we measure as T1 in the microtest on magnetic fields, they're smaller than the rates of the spin creation. So from the kinetic perspective, we create polarization faster than it fans out due to T1. We can play some other tricks, and again, the name of the game here is to be able to polarize not just the bound, but also free pyruvate, because here we now see two peaks. We're doing it at a different temperature, and here we show the interplay of water as an additional co-ligand to be able to push polarization to even higher levels. And at the moment, our kind of like record for our standard conditions is approximately 13% polarization for free pyruvate. Can we polarize other molecules? Yes, we can. This is an example of being able to do alpha-ketoglutarate, which is structurally similar to pyruvate. And again, we see very similar dynamics in terms of temperature sweeps, magnetic field sweeps. The build-up rate is again overpowers the rate of this spin destruction. And in this particular case, we are able to demonstrate that we can achieve 17% polarization. Another important message here is that this is very site-specific polarization technique. So here we're polarizing C1, we're not polarizing C5, we're not polarizing C2 at all. Why does that matter? It matters for biomedical applications where you may have potential overlap between different metabolites and the background signal from the natural abundance molecules. I'm not going to go in these details, but this is very important for biomedical applications. We can obviously do polarization of labeled compounds in case of alpha-ketoglutarate. So this is the compound prepared by our collaborators from NIH. Polarization here is a little bit lower, 10% versus 17% that I showed on the previous slide. Here we believe it's the spin buff limitation. We have way more C13s compared to natural abundance, and this is the reason why it drops down. Last molecule to show is keto isocaprate. Again, structurally similar to pyruvate, and again, the takeaway message here is as long as you have this motif of alpha-keto carboxylates, you can have very good polarization because you can have very good binding, you can optimize the exchange, and you can push it to quite decent levels of polarization. As I mentioned, this device is also capable of being able to apply DC fields. And again, the whole point for this device, it's just the integration. It's just being able to have everything in one box. So here we're using pulsed fields, the approach developed by Warren and his lab. And here we show that we can polarize metronidazole using this exchangeable approach. We're pushing polarization to over 20%. And again, if we compare the two approaches, DC versus AC approach, we show that there is substantial improvement by approximately 1.6 times in the levels of polarization. So this is the reason why we're considering doing both, because in some cases you may be able to push polarization much higher. The reason why we're interested in metronidazole, it's antibiotic, potential hypoxia probe, no relaxation T1 here, 10 minutes for an O2 group, so it's quite remarkable that we can push the lifetime of hyperpolarized state for that long. I'm not going to go through some of the other displays. So what I was able to show you during my presentation is that most of the time we polarize and then we put it in the detector, 1.4 Tesla, just to be able to see what our polarization is. So one of the other goals that we have is, can we simplify the hardware from the perspective of having a very small pocket size NMR spectrometer? Again, I have to pull one from the pocket. That's the actual spectrometer. It's really tiny. So this is an example where we use pocket size NMR to be able to do polarimetry inside of our xenon polarizer, which has in situ detection capability. It has smaller F well, which sits underneath. This is our hyperpolarized signal, which we detect on a single shot. Then we switch the field, match the proton resonance to the same frequency, detect photons at the same frequency, calculate levels of polarization. So in this case, we're getting 22% polarization in our hyperpolarized xenon inside of the polarizer. Can we use it for other purposes? Of course. So this is highly an optimized setup, but just being able to do the feasibility studies. So instead of doing ex situ detection at 1.4 Tesla, we're performing ex situ detection of C13 hyperpolarized pyruvate in our tiny NMR tubes in an optimized setup, which we believe we will be able to optimize in the future. This is the spectrum of hyperpolarized pyruvate with a relatively small quantity of 18 micromoles. Again, showing the feasibility that you can actually do it, you can quantify it. We know that we are overestimating our levels of polarization here because the setup is far being from optimal. So the advantages here, it's a cheap and commercialized device. It requires almost no space. operates in kilohertz range, runs on USB power. You don't really need anything else. And everybody's showing their NMR spectrometers. I feel like we had to develop our own too. So thank you very much for watching, and I would really enjoy your questions.
Thank you very much, Eduard. I'm fascinated that you can buy oxygen at Walmart in this spray cans. But Matt, please.
So 2 questions. Are there chemical shifts for propane in vivo? Like, do you see any, like xenon style? Could you do CSI in the lung or something like that?
I would expect they would exist, but they would be most likely substantially smaller compared to xenon. And I think that would be very hard to utilize them, but I'm not going to bet.
I mean, what is the solubility in blood? Do you know? Roughly?
So solubility of propane is actually quite similar to the one of xenon.
Okay, yeah, that's kind of what I would have guessed. Good. The other question is, so you mentioned FDA approval is not required for those canned oxygen things.
That's right.
So what approval, like, is it consumer product safety thing? I'm just trying to think the sort of strategy through, right? So,
sure. Absolutely. So the reason why there is no FDA approval required for those oxygen cans is they can get away with FDA grade oxygen. I'm sorry, aviation grade oxygen, not FDA grade oxygen.
I see.
So, and aviation grade apparently is excluded from the regulation by the FDA. So it's a silly way to get away. For propane, yeah, we have to think about that. Propane is already FDA regulated, unlimited use in foods. Obviously, it would require change in approval for being able to do imaging studies.
So it's not about a device in the case of oxygen. It's about the stuff that's in the bottle that's approved for human consumption or whatever it is. And then the can is not a device.
And then the can is not a device, and then you can sell it in Walmart, right? So I think this is a brilliant trick.
It is.
We all have to learn.
Great. Thanks, Ed.
I guess my questions are kind of related to what Matt was asking, because I was thinking about, clinical translation, and is there any precedent for doing inhaled propane? Like, are there any safety data that exists? Like when we did xenon gas, we had the benefit of knowing that it was an anesthetic and it was very well characterized. And that really helped the ongoing FDA approval. So I was wondering about that. And I was wondering about dosing also, like, is there any way to control the flow out of the device where you could stop it and when you get to a certain target volume that a person has inhaled?
Excellent question. So doctors, yes, we need to be mindful about safety. So luckily for propane, because it's a gas which comes from the oil exploration industry, there is a lot of data. So one study that was done, which is kind of hard to believe, it's a 90-day patient, well, not patient, worker exposure study, where workers were exposed to 1% propane for 90 days, no issues. There are people who done studies for propane exposure to patients on a very large exposure, like they were given something on the order of 500 milliliters to a liter, systemically several different times, and that seems to be very safe. There is obviously issue with flammability. Remarkably, FDA doesn't mind that we use propane in the foods, which to me again is remarkable. But I'm not going to question their judgment.
Yeah, no, thank you so much. Yeah,
thank you.
All right, thank you very much, and let's thank Eduard again. And our next speaker is Robert Cooper from George Mason University about intrinsic atomic gradiometer for sensitive RF detection.
Maybe we'll go back a little bit. I'm honored to have so many people attend my talk. My name is Robert Cooper. I'm from George Mason University, just outside of Washington, D.C. So today I'm going to talk about intrinsic atomic radiometers and how they're used for sensitive RF field detection. So I'll just give a little bit of a flavor for how they work initially so you can understand the later parts of it with the intrinsic radiometer part. So basically there's an optically pumped alkali vapor which processes the spins and lets us detect the RF magnetic fields. So these are particularly useful because of how easy they are to tune. It just has to do with the alarm precession of the atoms. And they're useful for stuff like NMR and NQR because they can be tuned with the resonance frequency of the nuclei. And you can sort of match the alarm precession of the atoms with the resonance frequency of the nuclei and do this so-called double resonance at a distance. And if you want to hear more about that, you can see my colleague Darwin's poster at 125 later today. Find us walking around and we'll be happy to explain it. So one of the differences between NMR and optically pumped atoms is the density and the polarization. So conventionally, NMR is a really high density of atoms and a low polarization. But these are used as a sensor, so you can have a low density because it's a vapor and almost 100% polarization. So to understand how they work, I'll just give a few graphics of it. So you heat this potassium vapor up to 180 C to get maybe 10 to the 14 atoms per cubic centimeter. And then you can send in a pump light, circularly polarized, to polarize the atoms along the direction of the static field B0. And this pump light transfers the angular momentum to the atoms and puts them in an end state defined by the Zeeman splittings. And the B0 sets the precession frequency, as I've said. Then you can send in an RF field at the precession frequency, and it will slightly tip the atoms out of alignment. And then they'll start processing in this transverse plane. And then that can be measured with this linearly polarized probe beam, which is actually measuring the signal through something called Faraday rotation. So Faraday rotation pretty much just relies on this linearly polarized light going through a magnetized medium. So normally it's a solid. So they have this thing called a Verde constant, which sort of gives a relationship between the polarization rotation before and after the medium. So in a vapor, it works a little bit differently because it's all quantum mechanical, and the different precessions have different indexes of refraction. So you get the rotation that's directly proportional to the length of the vapor that it's going through and the degree of angle that the atoms are tipped at. So why use an atomic magnetometer? They're very good for detecting radio frequency and DC RF sources, and they are able to do this sort of mapping. So you can get a 2D image, or I guess a 2D vector measurement of the magnetic fields in the area. And they can be used for frequency sweeps because they're so easy to tune. You just have to change a static field and the resonance frequency changes with it. For me, that just involves turning a knob, and it's extremely easy. And you can probably even just automate it completely if you wanted to. And as we've done before, you can detect local signals from zero-foot NMR, NQR, from like explosives, counterfeit pharmaceuticals. I know TSA even has an interest in it as well, because it's not invasive and it doesn't rely on a sort of metallic or magnetic source. You can do the non-magnetic detection as well. And it's great for suppressing large background noises, like common mode interference, like from a radio station, as we've done in the past. We do the unshielded work. So we had previously a very, very large magnetic field from a local radio station that was just ruining all of our signals, and we were able to do some subtraction to get rid of it. And another benefit is below 50 megahertz, they are intrinsically more sensitive than coil detectors, and they're not coupled with anything in the environment as well. So this is just an example from a previous paper. You can see here we have 4 sensors in an array, so you can see the red lines are the field vector measurements from the sensors, and these are just predicted field lines from a coil or a dipole. And you can see you can resolve the 2D vectors pretty easily. So about the intrinsic radiometer part of it, what is it? So you have these 2 voxels and you want to measure the signals on each of them. So ordinarily, you just add them together, so the light would go through both voxels and the signals would add directly. But if you add a wave plate in between them, you can actually subtract out the common mode noise or common mode signals, and then anything that's a gradient or differential mode. So like if you have a local source that has field lines that just deviate like that from a central point, the signals will actually add together. So here's a picture of the optical cavity that I have set up. So you can see the atoms are being pumped from both sides, and then you have this probe beam that goes in this M pattern. So it passes through the optical vapor in each cell twice, so 4 times total. And without the wave plate, these signals would just add. With the wave plate, the signals subtract. So the same signals subtract and gradient signals add. So yeah, so local fields would be nonlinear. So from like a source or a dipole, an NMR source or a dipole, they would just add together. And the neat part about this is since it's all in one channel, it evades the dynamic range limits of your equipment. So you can make a measurement without saturating your spectrometer or whatever lock-in amplifier or whatever device you want to make the measurement on. And this is just an image of my setup. So I have this copper mesh that's acting as a sort of pseudo Faraday cage. There's big holes in it, so it's not perfect. But you have the pump beam coming in from both sides. You have the probe beam coming in the front, making that M pattern, as I said. The Helmholtz coils cancel out and set the Larmor precession frequency of the atoms. And then you have the oven that's electrically heated to get the right number density. So how the optical rotation actually works is, I'll just go through it visually first before I go through the math part. So when you go through the first voxel, you can measure a signal through the Faraday rotation. And then it goes through the wave plate, and then it flips the polarization of the probe beam around the fast axis. And then when it goes to the second voxel, depending on the sign of the signal, it's either negative or positive for the same signal. And then when it goes to the wave plate again, you can see how a positive signal would go back to 0 rotation. So common mode, that would be the example of the common mode signal subtracting. And then when it rotates to the right over here, that would be an example of 2 gradient signals or 2 oppositely signed signals adding together with the wave plate. So we did this sort of modeling doing Jones matrices. And these are just the operators that you would do to do the math of it. But one thing I want to emphasize here is how we can write these in terms of Pauli spin matrices. So we can define the wave plate operator in terms of a Z Pauli spin matrix and the Faraday rotation in terms of a Y Pauli spin matrix. And this term theta here, which is just the retardation from the wave plate components, just determines how much the polarization of the light is rotated. And this is the total rotation. So you go through cell 1, then the wave plate, the cell 2, then the wave plate, and that's the final rotation of the whole system. So I thought it was neat that we could do this in terms of like a famous NMR paper, because they do the same exact math. The same math applies to NMR pulses as it does to this optical rotation that we're doing. And it's nice because we can do it with, we can either do it numerically if you just want to get the result, or you can do it analytically if you sort of want to get a flavor for what's going on. So we do this expansion for time symmetric pulses and get this thing. You don't have to worry about the details of it too much because that's not the final result. But I did something bad here. I kind of snuck in this epsilon term, which is sort of an error in the wave plate that arises from either misalignments and like thermal changes in the wave plate that I didn't show before. But if you include this error, you can see, or if you delete the error, you can see that it all reduces down to this Y term here, which is just the subtraction that you would expect from 2 subtracting signals. But if you do include the error, you have this extra small term that adds the signals together that scale is proportional to this. And this is sort of our upper limit, or our limit on how well we can actually do the subtraction from the intrinsic radiometer. So how we actually tune them, since our signals are measuring vector components, they have this, you can have a real part of the signal and an imaginary part of the signal. So it's a quadrature detection. So you can assign one part of the signal to, say, the pump power, and then the other part, the imaginary part, to this off resonance to sort of tune them to get this subtraction to work out. And unfortunately, the sensors are different, so they don't have the exact same spin dynamics, so you kind of have to degrade one sensor in order to match it with the other sensor. But you can still get really good results even with that non-optimal tuning in one sensor. So we're able to get a subtraction of a factor of 390, which is, I think, really good. So this is just a signal, a gradient signal being applied first, and everything is normalized to this signal. So the units here are 1, and I left the scale here to show the noise later, but you can barely see it, but they add up to 1 with this very small signal. So when you throw on the interference, so this is almost 100 times bigger signal or interference. It's common mode, so it's the same on both sensors. You can measure the signal on the left and the right sensor, and they're oppositely signed due to the wave plate. But when you actually do the optical subtraction, you can see that the signal cancels down to way less than the size of the actual gradient signal that was measured. So what happens if you put them both on at the same time? You can see that the signal here from individual measurements is almost all interference. You would never be able to see the signal out of this, especially because we did it at the exact same resonance frequency at around 1 megahertz. So this is all interference, and there would be no way to tell. But when you do the optical subtraction, you can see the interference is almost completely subtracted out, and it's almost all the signal, the gradient signal. And this is all of them together, just so you can see the signal here is at 1. You can see the interference here. There's the subtracted interference, and the difference here is just a very negligible amount to measure. So the sensitivity, we're able to get sub-femtotesla sensitivity, which is phenomenal. Under one femtotesla per square hertz for an adding signal, and for a gradient signal with the intrinsic radiometer set up in the wave plate in there, it's 0.6 per centimeter. So to optimize this sensitivity is a lot of work. There's so many different noise sources, and these are the fundamental ones, not including the background interference just from the environment. So the main ones that I have to deal with are photon shot noise, but the spin projection and light shift noise are also big contributions if you have different setups. So I kind of broke this out in terms of the probe power and the number of passes that it goes to the vapor. Because these are the most accessible parameters for us, we can easily change the probe power, and then the number of passes is sort of a parameter that we set at the beginning of the experiment. And for me, I used a high probe power and a low number of passes, so I was limited by shot noise. But one of my colleagues, he has a setup where he did very low probe power and maybe 50 passes or 10 times more passes as I did, and he was able to get down to light shift noise, and photon shot noise was not his main contribution. So what's the point of knowing this? So we kind of want to optimize this or minimize this term, the noise term. So this is minimized when tau is equal to 1. And that will give us our off resonance probe wavelength. And this says that we should theoretically be able to get down to 0.2 femtotesla per square hertz. And I'm at 0.9, so we're almost a factor of 5 off of the theoretical limit by shot noise. Yeah, so as I said, the Faraday rotation that I'm measuring is actually deviating from the theory, and that's kind of a mystery that we're dealing with right now, because it predicts that I should be a lot closer to resonance than I'm currently operating at. Currently, I'm 0.5 nanometers away from the D1 line, but it says I should operate 0.2. So to conclude, I'll just say the gradiometers are excellent for evading the dynamic range limits on the equipment, because you can measure all the signals on a single channel. And we're able to reduce the noise by a huge factor. And we can actually improve this more, and we'll continue to improve it more as we are able to control the spin dynamics of our system a little bit better. And this would be limited by our wave plate error. But luckily for me, the temperature error is not a huge factor, so it's just the alignment that would be limiting me. And with these tiny 7.5 centimeter cube voxels, we're able to achieve sub-femtotesla sensitivity. So I just would like to thank my advisor, Karen, coworker Dave, Darwin, who's in the audience, and Jafar, who's not here, from George Mason, and our collaborators at Princeton, Nazi and Mike Ermalis. And then I would like to thank ENC for hosting, and for travel stipends, and then NSF as well for funding. That's it.
Thank you very much, Robert. So, oh, we do have questions.
This is really beautiful work. So key to the gradiometric approach is that each cell sees the same local field, right? So that sort of sets the spatial resolution, right? You don't want to make those things too large.
Exactly.
Right?
You got to have a symmetry.
Yeah. So have you thought about ways to scale this to like arrays of detectors? So let's say you want to do sort of volumetric measurements.
Yeah.
Right? So could you comment on that at all?
Yeah, great question. So in the past, we've had these arrays, like 4 different sensors, 2 very close and then 2 very far. So you can use the far sensors to determine the local noise, and then the near really close signals to determine the signals. And we've actually have a paper on that one. If you're interested, I can give it to you later. But they also do something similar with MEGs on the head.
So in that case, you wouldn't do, let's call it in-hardware cancellation. You'd collect all those signals.
In that case, yes.
Yeah. And so then that leads to my second question, which is there's a very interesting point about doing the cancellation in hardware gives you a higher dynamic range. What is the upper limit, let's say in the case that you described of the gradiometer in terms of saturating field?
So there's something called RF broadening for our sensors. So if you hit the RF broadening range, then the signals are no longer linear, so they won't cancel correctly.
Okay.
But that's a few nanotesla, or maybe 10, 20 nanotesla high.
Okay.
But anything below that range they're linear.
Great. Thank you.
Yeah.
Please.
Great talk, Robert. I just had some questions about the optical cells. So you have your alkali metal vapor in there. Do you have any like buffer gases? And if so, what pressures?
Yeah, so I don't know the pressures offhand, but with the whole cell is at an atmosphere pressure. But we do have helium and nitrogen as our buffer and quenching gases. And I have the numbers offhand if you want to talk to me after.
Great. And also, do you use any surface coatings in your optical cells?
No, actually. The surface coatings, like the RF coatings or AR coatings, anti-reflective coatings, typically, if they're inside the vapor cell, they react with the potassium. So those put a short lifespan on the cells. And I know my coworker has had a lot of issues getting the system up and running before the alkali vapor reacts with the cells, the cell coatings.
Thanks.
Yep.
All right, John, please.
And so you mentioned 50 megahertz as the crossover point in terms of sensitivity of coil versus these gradiometers.
Yeah.
Is that based on like the Savikov's paper with the search coil geometry?
I can't remember what it's a Ramallis paper, and I can't remember offhand which one it is.
Okay, and so I guess would you use the same sort of detection strategy for your maybe NQR measurements, where you would just have basically just the one coil putting up next to it?
Yes, I think so.
Okay.
Yeah.
All right, if there are no further questions, let's thank Robert again. And our next speaker is Omar Nassar from KIT with automated high-throughput nuclear magnetic resonance spectroscopy.
Hello, so welcome everyone for my talk. So first I would like to thank ENC for giving us the opportunity to present our recent result for enhancing the throughput of NMR spectroscopy. So currently NMR spectroscopy is limited for a single sample measurement, where a sample with a typical volume from quarter to half milliliter is loaded inside the magnet. Then matching and tuning is done to adjust the instrument for the frequency of interest. Then shimming is done to adjust the homogeneity of the B-node field. To get a feeling of how long of the time required to screen a batch of samples, so this is an example taken from a recently published material where they screened 300 samples in 120 hours. This results in the fact that NMR spectroscopy has a poor throughput, which results in a disconnect between the application that require screening large number of samples and taking advantage of this information-dense analytical technique. And one of the hot application that requires screening large number of samples is drug discovery, since NMR can efficiently resolve the binding of drugs to pathogens. However, in 2017, Pfizer declared that in their molecular library, they have more than 4 million compounds that can be potentially used as a drug. Several attempts have been done before to increase the throughput of NMR spectroscopy. The most important of which are the automatic sample exchanger. However, this approach still uses the conventional glass capillary. Also, matching and tuning and shimming is required between each two successive samples. Another approach is the flow-based NMR approach, where a flow tube is fed through the magnet. Then the samples are transferred inside the magnet through the tube. However, this approach still faces the disadvantage of the long dead volume of the sample, since the sample need to entirely fill the tube to make sure that it's filling the detection region of the instrument. Also, the flow line need to be cleaned between each two successive sample to prevent cross-contamination between the different samples. The flow-based NMR approach is a more promising approach, since in case of static sample, you require a recycle delay to make sure that the nuclei return to their equilibrium position between each two successive scans. However, in case of flow-based NMR, no delay is required, since you are always getting a freshly polarized sample. So if we adapt the flow-based approach, but instead of having a single sample in the flow tube, we can have a series of different samples separated by a segment of immiscible fluid. And then once we put this line of different sample under flow, we get a notification once the sample reach the detector inside the magnet, and then another notification once the sample leave the detector. We can get the spectrum of each sample separately. So the currently available NMR devices consist of the permanent magnet, the probe, and then which have on top of it the probe head or the RF detector. So microsystem technology give us the advantage to develop customized element. This element consume low power, which is important in our application here. Also, it's scalable. Micro devices are scalable in manufacturing when mass produced, and can be integrated with microelectronic, resulting in a smart devices. Also, in case of NMR, microcoil result or microdetector result in a higher sensitivity in case of limited sample. So we took the advantage of microsystem. We only replaced the microdetector by a custom built NMR probe head, which possesses a micro saddle coil and two flow sensor flanging this detector. We integrated two flow sensors so that we have the flexibility to run the NMR experiment by pushing or pulling the line of the samples. Also, it gives us the capability to measure the volume and the flow rates of the samples. The two sensors as well as the coil are built around a glass capillary, where the microfluidic tube is fed through this glass capillary, so we prevent any fluidic junction to not interrupt the flow. So this custom built NMR probe head is loaded on the top of a normal, the top of a market available probe head, and then the micro detector is connected as normal to the NMR console, but the flow sensor, the reading of the flow sensors are converted from an analog data so that we can transfer it outside the magnet to a digital data, and then it's connected to a simple micro shelf available microcontroller unit, which in turn synchronize the NMR acquisition so that we can separate the spectrum of each sample. So here you can see the NMR software running for a line loaded with 6 samples separated by 6 oil plugs. So this is synchronized automatically by the microcontroller, which get the signal from the sensor and synchronize the NMR acquisition. And as you can see here, the system successfully separated the FIDs of the 6 samples with different volume, as well as which is not visible, the FIDs of the oil plugs. But since we are using fluorinated oil, so it's kind of separation between the spectrum of the different samples. So now I will briefly explain the 2 main components which we added to the system, which are the RF detector and the flow sensor. So for the RF detector, we adapted the saddle coil geometry because it generates a B1 field perpendicular to the coil geometry, so it can be aligned with the B0 field, so it allows the flow of the sample. And by optimizing the geometry of the coil, you can get a better performance. So here you can see by changing the dimension of the geometry, we can change the distribution as well as the sensitivity of the B1 field. Also the effect of the coil tracks on the homogeneity of the B0 field. So by optimizing the geometry, we choose this value where it have quite a relatively high sensitivity and least effect of the B0 homogeneity, so we can easily shim the coil, because the shimming process for the microcoil is not an easy process as in conventional coil. That's why you need to consider the effect on the B0 field. And here you can see this was the developed microcoil, micro saddle coil. So here you can see the measured loaded quality factor. It's around 50. And here's a single scan for a water sample. So it have the full width at half maximum is below 2 Hertz. Also, this you can see a single scan spectrum of a water sample having the 250 milliliter sucrose and 30 milliliter TSB in a 500 megahertz magnet. So you can see that the coil, the microcoil, which we developed ourselves, successfully resolved the J coupling. Also, the limit of detection at the 500 megahertz around 1.19. So if we normalized it to 600, so that we are able to compare it to other coil. So here the active sample volume. So this microcoil have a sample volume of 3 microliters. So in comparison to other coils having the same sample volume, we are doing far better, and in general we are reaching the limits. So this is regarding the detector, so the saddle coil. And for the flow sensor, we adapted a design. It's called interdigitated capacitive sensor. So it's not connected, and then by providing a voltage on both terminals of the sensor, it generates an electric field. This electric field is sensitive to a parameter in the solution. It's called dielectric coefficient or relative permittivity. So here you can see the distribution of the electric field in case of the oil we used for the separation, and in case of aqueous solution. So the sensor can easily detect the difference between the oil and the sensor. That's why it can synchronize the NMR acquisition. And here you can see the sensor reading in case of having 3 aqueous samples separated by the oil block. So these are the sensor reading when they are filled with the oil, and then here the sample enter the first sensor and enter the second sensor, and then the timing we can use for measuring the volume and the flow rate, and then we use this to synchronize or start and stop the NMR acquisition, so that we can save the scans in a different memory location. So by the end we can the spectrum for each sample separately. So as you can see, this flow sensor differentiate the sample or sense the difference between the sample based on the dielectric coefficient. So water and oil, they have a relatively different dielectric coefficient. That's why it was easy and clear that the sensor will be able to differentiate between these different solutions. However, also the sensor was able to give different signals in case of solution having a relatively close dielectric coefficient. So the dielectric coefficient of ThOD is the closest to water, and we still could see the difference. So we are able to see the different sample. Also here you can see the air have a dielectric coefficient of 1. So even if you have air bubble inside the flow line, we still can detect this with the flow sensors. So I know this is quite off the topic, but the way for fabricating these sensors and detector is done by a well-developed microfabrication process. It's called photolithography, where you have a layer of a flexible polymer, usually Kapton, because it's compatible for electronic devices. And then you have a copper layer on top of this Kapton film. And then we use a photosensitive material with a UV exposure to structure the material. And then we structure the copper layer on top of our substrate. That's why, as I mentioned, micro devices are scalable in manufacture. So you can see here, this was a batch of sensors and micro detector that was developed or fabricated in a single day. So to validate our system, here are different experiments that we made using our system. So we filled the flow line with the samples of different volume, because since we have 2 sensors, then we are not limited to the volume or even the flow rate. So you can see here the system successfully separated the FIDs of the different samples. So here you can see the FID of oil, and then sample, and then oil, and so on. And these samples having the different volumes, because we are not limited by the sample volume. And this, you can see the change of the SNR by increasing the sample volumes. So we achieved the sample, a flowing sample, the minimum flowing sample of volume 40 microliter, which in our case, it's a 5 centimeter sample plug. And then also we have flow rates up to 12, or even we achieved 30 millimeter per second. So we can get the spectrum for a sample going 3 centimeter in a second. And then, we have done the experiment in a 2 way. The first way by using this automatic acquisition system, and then another way, the old conventional system where you switch it on and off once you see the sample inside the magnet, and you switch it off when the sample leave the magnet. So here you can see the spectrum in case of the blue one, in case of the automatic sample triggering. You can see that you only get the spectrum from the sample, but for the conventional way, it's averaged with the spectrum of the oil, because you cannot, so manually you don't know when the sample will be inside the detector, so you just switch it on and switch it off once the whole line leaves the magnet. That's why it's averages with the background signal of the oil. Another experiment, we filled the line with 9 samples. Aqueous samples of different glucose concentration. We started with 1 milliliter and ended with a high concentration, 1 millimole and 1 mole. And we done the experiment back and forth 4 times, and then you can see we get the non-linear relation between the concentration and the SNR, which proved that there was no cross-contamination. And this is also one advantage of the oil plugs, of these oil plugs, so they clear the line. That's why the sample doesn't get mixed. And here you can see that we done the experiment for 9 sample plug separated by 9 oil plug, because also you can load the oil plugs with measurable molecules in just 3 minutes. And to prove the concept, we loaded the line with a completely different sample, so a group of beverages, and you can see that the system is still be able to separate the FIDs, and it generate the spectrum. So with that, I would like to conclude my talk. So we are in a very high need for increasing the throughput of the NMR spectroscopy to be used in several applications, especially drug discovery, which we are working on now. So actually, what's done by our chemistry collaborator, they loaded the sample inside microfluidic tube. So this you can see it's a 100-meter tube loaded with a 400 samples separated with 400 oil plug. And what we do, we just take the tip of the flow tube, we feed it through our sample, which is plug and play ready with market available NMR system. And then this is the probe head, which is loaded inside the magnet. And this is the microcontroller unit, which is outside the magnet for the automatic synchronization. So even with quite big volume and quite low flow rate, we enhanced the throughput by a factor from 150 to 200. So if you run the system at the limit, so the minimum volume and the highest flow rate, you still get an enhancement of around 600. In this work, the loading of the tubes is done manually, which is a really painful process. So what we are doing now, we have developed a kind of a robotic system which automatically fill the samples by loading the different samples and the separation oil plugs. And then also, in case to increase the throughput, this can be scaled up by a factor of a number of a parallel channel. So instead of having one of our channel with the sensors, you can have several of these parallel channel which scale up your throughput. Yeah, so at last but not least, I would like to thank the NMR group at Karlsruhe Institute of Technology in Germany, as well as the funding support. And I would like to thank you for your attention, and I will be happy to take your questions.
Thank you very much.
Just a quick question. I didn't understand near the end, you said that the sensitivity to background was reduced in the automatic system. So I thought in the manual system, you kind of wait until you see what you get, the sample is appropriately positioned, and then you do your shot.
Yeah.
Why does that have a difference in background?
Yeah, so the conventional way is to have a very long block so that it once enter the magnet. So you see the tail and the tip of the sample, you start. And so this is what we haven't done here. So since we need to compare since we need to have a comparison here, so it's the same single plug, which is 4 centimeters. So it's a 4 centimeter plug. So in the case of automatic, we just run it and the system automatically start and stop at the end and tip of this plug. But in case of the manual, it's still filled with oil and then there is just this small plug. But once we see this plug entering the magnet, we start the acquisition. So at that moment, we are collecting only for the oil, and then we collect the sample and then again the oil. And once we leave it, we see it leaving the magnet, we stop the acquisition. That's why it's averaged with the oil.
I see.
Before, it was a very long plug.
So this is, so it's sort of a different situation, right? I mean, it's not like you were using the samples loaded just like this. You're talking about using the previous system.
Yeah.
Okay, thank you.
Yeah, thank you very much.
Any more questions?
I have a comment and several quick questions.
Yeah.
One quick question, you don't get cross-contamination of your samples?
No, so so actually the oil which we used here for separation, it's called FC43 oil. It's an oil which mainly used for electronic devices to cool it down so they don't have any electronic properties because they don't carry any static charge. Also, they keep the cross contamination between even the electronic component as minimum. So as this oil plug are moving, they are pushing completely the whole sample. So you can see here we have an aqua sample with 1 millimole and another sample with 1 mole, and we still push the whole line back and forth, running the experiment 4 or 5 times, and they never mix together.
Thank you. So second one, you mentioned that with the sample changers, you will need to rematch your probe. Now, do you have to rematch this probe because you have different salinity of your sample? And how you do that?
No, since we are the samples here are in a micro sample volume, so they don't have that much of effect on the matching and tuning of the probe as well as the shimming. So the whole line, once we shim it using the first sample, so the first demo sample, and then we just run the whole experiment without changing the matching and tuning as well as the shimming.
Did you try different salinity? Because this one was sugar, right?
Yeah.
But how about?
No, so we still didn't cover a huge range of samples, but the one which we tested, so we didn't need to change the shimming or the matching and tuning.
Okay, and a comment: if your sample moves fast enough, then you can take advantage of the fact that for each next FID, you get fresh samples, so you can actually pulse faster. You can check publication by Kevin Donovan and AJ Shaka from about 10 years ago.
Okay.
They did advancement of tube, and so you could increase your speed.
Yeah. Okay. Yeah. Thank you very much. Thank you.
All right. Thank you very much. Let's thank Omar again.
Thank you. Yeah, thank you.
And our next speaker will be Sven Bodenstedt from the Institute of Photonic Science, talking about decoupling of spin decurrence pathways near zero magnetic field.
Thank you very much for this very kind introduction, and thanks for the organizers for giving me the opportunity to present our recent results. So this project is a collaboration between my institute, the Institute of Photonic Science in Barcelona, as well as the Max Planck Institute for Multidisciplinary Science in Göttingen. Let me motivate this problem of spin decoherence near zero magnetic field by talking about isotopic substitution or isotopic labeling. I mean, I guess most of you have done this in one way or the other. There are many ways how to do it and many reasons why you should do it. And there are many isotopes where it makes a difference, like the spin properties change as well as other properties. So for now, let's focus just on hydrogen and deuterium because it's very popular and it's also a very interesting example. At high field, there are many reasons why you want to do that. You could also you could simplify the spectrum by either just reducing the number of protons you have on a molecule, or by somehow increasing or improving the dispersion of the signal. You could use the deuterium as a field log, as well as you can restrict the pathways for transferring spin order, depending on if you have like power hydrogen or fit-based methods. But also it reduces the magnitude of any dipolar coupling, and therefore it could actually make your could reduce the dipolarization rates. But you may think about that, well, the deuterium is still a spin 1 system. So it is a rapidly relaxing system. It has a spin 1, it has a quadrupolar moment. So you may think about if you actually could induce any kind of relaxation by replacing hydrogen with deuterium. And for high field, the good news, well, it's not a news, but the good message is that typically it is not a problem because the difference in dry-magnetic ratio is just so huge that they're automatically decoupled. Unless you have like some special cases, like for example, you can have singlet states with very long coherence times. This could be an issue, but typically at high field, you should not carry about that. On the other hand, and that's what this talk will be about, if you go to ultra low fields, and ultra low fields in this context are microtesla fields, so fields with Lama frequencies of tens of hertz, or in general fields where the J coupling is in the same order or even larger than the Lama frequency. What happens there? So you still may have similar motivations to do that. One reason is that even for even for very symmetric or simple molecules, if you do zero field spectroscopy, the spectrum gets quite complicated. So you may think about maybe isotopic substitution can simplify it somehow. Is that an option? Or if you think about like hyperpolarization methods that work at ultra low fields, where you want to somehow restrict the pathways of the transfer of spin order, you may think about what does deuterium or like the substitution of deuterium does in these kind of systems. And here you definitely have to think about the effect of relaxation, because if you look at what you need for scalarization, especially of scalarization of the second kind, you need scalar coupling, which you typically have between a slowly and a fast relaxing spin. This is exactly the system that I would like to discuss. So the model system for this target will just be like a hydrogen atom, a deuterium atom, which is coupled in a magnetic field. This is the most simple system you could think about. And if your field is low enough and the J coupling is high enough, then these become strongly coupled spins. And then you would expect scalarization to be quite dominant. And that's actually what we observed. So here we have a different spectra of ethanol in ultra-low fields. So I think that the highest field is about 2 microtesla, which is like about 80 hertz of Lama frequency. And on depending which hydrogen or which protons you replace or substitute with deuterium, you see a significant change of the line width. You have to be a little bit careful interpreting this, just the line width and the spectra, because there are many contributions on the line width in general. But what you see is that the lines are getting broader, and this seems to depend on the amount of deuterium, or like on the deuterium you have in the system. So the topic of the talk will be, or the question I would like to answer is, would it would be quite nice to get rid of the coupling between the hydrogen and deuterium, like just getting rid of the J coupling term here, and how this could be done at ultra low fields. Let me first show you that this is actually possible. So what we see here is a spectrum recorded at about 5 microtesla of the same molecule that you saw on the previous slide. So we see a huge peak for hydrogen at about, I think, 180 hertz. And we see a smaller peak for deuterium. Don't bother too much, this is out of phase at the moment, but we see that we have both signals. And we have a J coupling between the hydrogen and the deuterium, which is about 1.2 hertz. And if you look at the T1 relaxation rate of that molecule as a function of the B0 field, you can see that at high fields, so to say, that it feels like above half a microtesla. This seems to be a flat line. It seems to me not affected by scalarization. But if you go to the regime where the Lama frequency is getting close to the J coupling, you see a drastic increase in the relaxation rate. And if you decouple that, you see that you get a flat line, basically. So if you apply a decoupling sequence during the free evolution relaxation delay, during the relaxation delay, then you can see you can actually efficiently get rid of that coupling. The question is, how do you do that? At high field, that is, is well known as a quite simple task. You just have to look at the J coupling Hamiltonian, and you see that if you flip one of the spins, either the Z or the I spin, and do repeatedly do like a sequence of pi pulses and average the Hamiltonian to the first order, then you effectively get rid of that term. A zero field is a little bit more complicated because you have to consider all vector components of the J coupling Hamiltonian, and just applying pulses along one axis wouldn't be enough to decouple it efficiently. But what you can do is, like, you can apply pulses along different axes, like for example X and Y, and if you do that in the proper way, like if you just apply the standard XY4 sequence and average it out to the first order, then you can get rid of that term. And if you play a little bit more with that, so if you just apply pi pulses on one pulse, you can get rid of the Zeeman term as well as the J coupling. If you apply that on the other nuclei, you can get rid of the other Zeeman term. And if you decouple both, or if you apply pi pulses for both spins simultaneously, you would keep the J coupling term, but you will get rid of the Zeeman terms. So you would effectively create a zero field, even if you're not actually at zero field. Let us get that one step further. So if you just go from the operator picture to the super operator picture, then we have the two terms we had in the previous slide. So we have the super operator for the Zeeman term. We have the super operator. Yeah, these are the Zeeman terms. We have the super operators for the J coupling term. But we can also look at dipole-dipole relaxation as well as the cross relaxation terms. So this is in a spherical tensor basis, and I think they are sorted by the projection index M just to somehow get like a block diagonal shape of these matrices. They don't. They only show like non-zero elements, so don't think that all of these components have the same amplitude. It's just all the elements which are non-zero are like highlighted here. And then you can like do like a similar, you can have similar thoughts like in the previous slide. So if you just apply xy4 on one spin, like the I spin, then you would get rid of the J coupling as well as the Zeeman interaction for that spin, but you would also get rid of the cross relaxation term, which is quite important. If you do xy4 on both spins, so if you flip both spins at the same time, you would keep the J coupling, you would get rid of both Zeeman terms, but again, you would slightly modify, no, this would actually be not modified here, the dipole-dipole relaxation would be slightly modified, but the cross relaxation would still be there. So the question is, how do you actually apply selective pi pulses or pi pulses on both spins at the same time at zero field? Because at zero field, there's no such thing as resonant pulses. At zero field, like all the spins or all the Lama frequencies are close to zero or very much close to zero. So the way you apply pulses is just by applying a DC field. So but then the question is, yeah, how do you apply like a proper rotation on one spin and by ignoring the other spin, or how do you apply like a pi rotation on both spins? We can try to solve this issue by looking just at the ratio of the gyromagnetic ratios for both spins. And for deuterium and proton, that's about 6.41. And for now, just assume that this is about 7. We come back to that later, that it's not exactly 7, but for now, let's assume that. So in other words, if you apply a 7 pi rotation on protons, that would effectively be a pi rotation on deuterium. So you just like have your spins like aligned along the z-axis, and then you apply a field along the x or the y-axis, and then you just apply the field for a certain amount of time, and that will effectively rotate both spins. And if you do that, so what is plotted here is just on the x-axis, the length of the pulse, the length of the pulse. The blue one is the protons, so you see you actually apply Rabi oscillations with that, and the orange line is the same for the same amplitude of the field for deuterium. You would see that you get a much slower oscillation, but still, And if you look at exactly this condition where you apply a 7 pi rotation on protons, you see that it is almost a pi rotation on deuterium, but not exactly. But also for that, there are solutions in high field. You can use composite pulses to make that somehow more robust. And if you do that, so if you just reduce, or if you just replace the normal pi pulse with like something similar to a pi over 2 pulse on 2 different axes, you can make this region much more flatter, and then you can see that basically, if you just use the right pulse duration, you can apply very nice pulses for both spins at the same time. And that's how we basically do it. The last question is, how do you detect all of that? And here I'm very grateful that we had a talk about atomic magnetometers, so I don't have to explain a lot here. So I will go very briefly on that. So this is the experimental setup. Everything here is home built. So the main challenge is to get rid of all the residual magnetic fields, especially DC. Passive magnetic shielding does a very good job here. So we just use a 3-layer new metal shielding with another ferrite layer. We have a solenoid in between, which provides the B0 field up to a few microtesla, which is good enough for our application. And then we have a rubidium vapor magnetometer. I won't go into detail there because we just had a talk about how they work in principle. But yeah, basically they're very good for detecting DC to RF signals up to a certain frequency. And I'm also very grateful that we had a talk which showed how greatly tunable they are. So what we did here is like we just basically just showed like that we can easily tune the sensitivity or the resonance, the sensitive frequency by applying an offset magnetic field, and that allows us to be sensitive at different magnetic fields. We're mostly sensitive for this application. We're mostly interested in that regime of a few hundred hertz because it's the most sensitive region of our magnetometer, reaching not sub-femtotesla, but like 10 femtoteslas for our sensor. And we to give you an idea about the sensitivity, I mean, it's not comparable to like what you're used to at high field. But if you polarize like a sample of the size of a single vesicle of an orange at 20 millitesla, so 20 millitesla is a really, really low thermal polarization, and you have a sample volume of about 10 microliter, we get a signal which looks about that. So that just gives you an idea about how good the sensitivity is. It's not perfect, but for our applications, it is more than good enough. Let me also tell you a little bit some other applications we can do this setup. We did a lot of work on nuclear magnetic resonance dispersion, which is there are a lot of applications where you want to know how the relaxation rate changes for different lambda frequencies, and we were able to push existing techniques to the super low field regime. So we can actually now do the experiments up to tens of nanotesla, tens of hertz, or even just a few hertz. And we are also able to do this within metallic containers, which offers also some new applications, especially if you think about like chemical reactors or high pressure sealed samples. We can do experiments with that. We also did some spectroscopy work. So you can look at systems where you, like this is like trifluoroethanol, where you have fluorine atoms and hydrogen atoms, which are coupled by J coupling of about 9 hertz. And you can try to, you can think about what's the best, or what is the highest possible, or what's the best field to get the highest possible accuracy in determining the J coupling. And it seems it's not high field, it is not low field, but it seems it is somewhere in between. So we found like an optimal field, which is of lambda frequency of a few hundred hertz, and there we got almost sub-millihertz precision in that coupling constant. And then we can also combine that, so we can also do spectrally resolved relaxation, where you just like have a molecule. Here's a methanol, carbon-13 labeled, and we look at the relaxation rate as a function of the field. With that, I would quickly like to introduce where I'm from. So I work in Spain, Barcelona, at the Institute of Photonic Science. So this institute, so every experiment you want to do there requires you to use at least one laser, because it's the Institute of Photonic Science. We solved that issue because we still wanted to do NMR experiments. But we solved this issue by not using a high-field magnet, but by using atomic vapor cell magnetometers. They need lasers, so we were allowed to do our experiments there. Otherwise, I think we wouldn't. Yeah, they would have denied entry. The other institute that was part of that is the Max Planck Institute for Multidisciplinary Science, the Institute of Stefan Glöckler. No, just a group of there. I think they're most famous or popular here because they were very lucky and got one of the first groups that got one of these 1.2 gigahertz systems. I think they got it in 2020, so more than 2 years ago. Fun fact, it wasn't used for any of the experiments I was presenting, but just to let you know. And with that, I would like to thank all of you. I would like to thank my team at ICFO. I'm the only one who forgot to put the mask off during this group picture, and I don't think there will be a group picture anytime soon. So I think that's how I have to live with that. And yeah, let's just yeah, thank you all for your attention. And
Great, thank you, Sven. Are there any questions?
I have a quick question. So beautiful work. You have a detector to be able to do the detection in the microtesla magnetic fields, right? Can you still figure out a good way to apply your pulses if you don't have a detector, but you still want to apply the pulses?
Can you repeat the question? It's quite hard to understand you.
So you have a kind of like a luxury of being able to sense stuff inside of your device at these nanotesla magnetic fields, but you also apply pulses during all of these spin manipulation. So let's say you want to apply the pulses to be able to get all of these fancy effects that you're talking about, which is quite brilliant, quite nice. But let's say I don't have a detector. Can I still do that?
Oh, yes, I think so. I mean, yeah, you only have, I mean, we could be quite, I mean, the only challenge will be to calibrate these pulses, I would say. But in principle, yeah, nothing will stop you from doing that at zero field. Yeah.
Hi, great talk. So for your magnetometers, do you use continuous pumping or pulsed?
We use continuous pumping and continuous detection. Yeah.
Okay. Do you find that has any effect on like your T2 times?
Of the magnetometer?
Yes. Yeah. Sorry. Of the magnetometer.
I mean, it depends. So we designed this magnetometer to be an as good magnetometer at DC as well as like low RF frequencies. So if you want to have a better RF magnetometer, I would probably not use that approach. For DC, I think it's still one of the was the approach which gave us the best sensitivity. So we somehow try to find the balance between being good at DC as well as being good at RF, which in the end lead to a magnetometer which is neither a good RF magnetometer or a DC. But since we require this tunability, it is a quite good compromise. Yeah.
Very nice work. Isn't there any reason to go beyond XY4, or is XY4 just really good enough? Like, is there a reason to go to these higher order versions of these pulse sequences?
We tried all the pulse sequences. I mean, XY4 worked the best. That's what I would say. We didn't do a detailed theoretical analysis about if there are better pulses or if they are if the pulses we are using right now are the best. No, I mean we just tried. We went with the most simplest pulses and we tried them out, and they worked for our application. But yeah, if you want to have if you have different spin speeds, for example, if you think about not having protons and hydrogen, but protons and deuterium, but like protons and nitrogen, which has a much different ratio of diamagnetic, diamagnetic ratios, then maybe you have to, you have to change your strategy. But for us, I mean, it also depends on how homogeneous your pulse calls are how robust you have to be. As long as the additional relaxation, which is due to the pulse errors, is not significant compared to the relaxation of your system, I think then you're good.
Thanks.
All right, let's thank Sven again. And with this, we're coming to our last speaker, Kerstin Münnemann. She is joining us remotely from Kaiserslautern, from the Technical University in Kaiserslautern, and talking about how hyperpolarization enables fast reaction monitoring of diluted systems.
Thank you very much for the kind invitation and for having me even remotely. I really apologize that I can't be there in person. So my talk will be about how hyperpolarization can help us to enable fast reaction monitoring even in diluted systems. So if you are thinking of process monitoring or reaction monitoring, a normal setup will look like that. You have a reactor, and then you just want to continuously drive a sample loop out of the reactor and feed it through your detection spectrometer and then feed it back inside the reactor. If you think of fast reactions, the sample loop should be as small as possible because you don't want to have high transport volumes, and you also want to have a very fast transportation time. In our lab, we are doing that now frequently by benchtop NMR devices, which we have seen also quite often during the session, because you can just bring them very close to the process that you want to measure. However, if you think of flow NMR, benchtop NMR devices has also some disadvantages. And that is, so in flow NMR, the prepolarization of your sample before it enters the RF coil for detection, of course, depends on the flow rate and on the T1 of your sample. So here we did just different experiment with a small capillary and water, and you see that with higher flow rates, we have a very high drop of the relative polarization, because in this benchtop NMR devices, we have only a prepolarization length of about 10 centimeters. So that's very tiny compared to high field magnet. But if we think of fast reaction monitoring, this is exactly the flow rates that we are interested in. Okay, and hyperpolarization will help us here very much for the monitoring of fast reactions, because then the prepolarization doesn't play any role anymore. So this talk is organized into two parts. First, I want to speak about Overhauser DNP that enables fast flow NMR. So I think throughout the conference, we had many DNP talks already. Here we are dealing with Overhauser DNP that takes place in the liquid phase. We dope our sample with electron spins and transfer their polarization by on-resonant microwave irradiation on the electron spin Lambda frequency to the surrounding protons. And we get a quite decent signal enhancement. Of course, they are not that high than in solution DNP, but worthwhile doing the experiments. The experimental setup that we used in this work looks like that. So we have a Halbach magnet where we do the ODNP at a normal X-band frequency on top of a 1T benchtop NMR spectrometer. So in our ODNP unit, so the heart is a fixed bed with immobilized radicals, and in the middle of the setup, of course, there's a microwave cavity. And to use here immobilized radicals is very, very important, because after hyperpolarization happened, of course, we have to shuttle our sample down to the benchtop NMR. And if we, so the T1 times in contact with the radicals are quite short. So if we wouldn't use immobilized radicals, we would lose all our hyperpolarization during the transportation step. Okay, we used a demanding test case and measured this flow NMR experiments in a very tiny 250 micrometer capillary. And I will show you now a better look to the immobilized radicals. So for aqueous systems, we use a system that is very well known in the literature. But for organic systems, we did now design a new immobilized radical matrix that is based on CPGs. These are controlled Pore glasses, and we use them because they are perfectly chemical inert, and we still have good ODNP parameters like high mobility of radicals and an optimal access to target molecules that we want to have for ODNP. If we now have a look at the results of the flow measurements in the benchtop NMR, so the blue signals are thermally polarized and the red ones are the hyperpolarized one. You see that with very tiny flow rates with a flow velocity of around 0.08 meter per second, we still get a kind of decent pre-polarization, so we are still able to detect thermally polarized signal. But when we increase the flow rate, you see, of course, our signals start to vanish. Whereas because the ODNP buildup happens with a very rapid T1 times of the in contact with the radicals, of course, and we get enhanced signal due to the polarization transfer from the electrons, you see that we get spectra with a completely different signal to noise, so they are much better. So this is the peak of acetonitrile, and that's the one of water, and you see the water peak is much smaller here, and that is because at these tiny flow rates, the hyperpolarization relaxes already during the transport step. So if we go to higher flow rates, you see that this problem vanishes and we get the same signal to noise more or less for acetonitrile and water. You see that the line of acetonitrile decreases a bit here, and that is because at very high flow rates, we don't have the perfect build-up time for the acetonitrile anymore, and that is why that peak decreases at high flow rates a bit. So for doing reaction or process monitoring, of course, we want to have highly reproducible experiments, and with that kind of device, we can have that. So if we have here a stream of thermally polarized liquid, and then we switch on the microwave, we see that we get a hyperpolarized signal, and after some initial heating problem, we have a quite stable signal. Still, the quantification for getting the concentration of the different molecular species is quite difficult when you do hyperpolarization, and especially if you do ODNP. We are able to account for the T1 relaxation by computational fluid dynamics, but still we have the problem that we have different enhancements for different molecules. That depends on the different correlation times of the specific molecules with the radicals, and that's an inherent problem in Overhauser DNP. So some groups are doing molecular dynamic simulations of that, but if you think of very complex mixtures, that will be really, really challenging. So we are trying to do that, but at the moment we are trying to solve the issue more by means of calibration. So as a summary of the first part, we can measure now spectra with a very decent signal to noise, even at very high flow velocities. And now we are working on really doing a quantification of the hyperboreized signal to have a really application for reaction monitoring. With that, I come to the second part of my talk. That will be about parahydrogen-induced polarization, where we want to, with which we want to do also reaction monitoring in benchtop NMR systems. We heard the FIP theory already in Edward Checkman's talk at the very beginning of the session. So I just jump over it here. So we have an unsaturated moiety, where we add parahydrogen by a catalyst system. We are using mostly rhodium or ruthenium catalysts, and then you end up with hyperboreized protons in your molecule, and depending on the field strength where you perform the experiment, you end up with an antiphasic pattern separated by the J coupling, or in Altadena, the antiphasic pattern is separated by the chemical shift. Of course, relaxation, with relaxation, you lose all your hyperpolarization, but you can, of course, like you always do in hyperpolarization methods, you can resume on putting your polarization on nuclei with a longer T1 time, like for example, carbon-13, and that you can do by pulse sequences like ENEP, or you can do it by level anti-crossings and magnetic field cycling strategies. So if you want to do reaction monitoring, it's good to have an initial test case to see which kind of signal to noise you get, and if we get a high peak cancellation because the shimming is not so good, and stuff like that. So we choose 3 different very well-known FIP reactions to have a look at that. So one is the one with dimethylacetylene decarboxylate, one started with hexane, and one starts with hydroxyethyl acrylate. So our experimental setup for this simple test is very, very easy. So we just have a 5mm tube where your reaction mixture is inside. We charge that with parahydrogen, heat it to 60 or 80 degrees C. Then we do a vigorous shaking to mix the parahydrogen inside the liquid, and then we just place it into an NMR spectrometer. And even with that very, very simple setup, you see the full power of the FIP hyperpolarization. And so why is the hyperpolarization so good? Because we start in parahydrogen with a spin order that is very close to unity. And of course, the thermal polarization in benchtop systems is not that great, and therefore you end up with really high enhancement factors. And we did that also for carbon-13, and but we didn't use any pulse sequence for putting the polarization from the proton to the carbon at will. We just let the system evolve at Earth field, and then we just put it inside the magnet, and then we end up with this very great single scan carbon-13 spectra. So the thermal reference, because it's here a very diluted system, we weren't able to measure the thermal reference with the benchtop system anymore, and we measured that in a high field 400 megahertz system instead. Also for hexene, as everyone knows, the FIP experiment works great, and we get also really high enhancements. And the same is true for the hydroxyethyl propionate. Here we performed the experiment in different solvents like methanol or D2O. And for the reaction monitoring, we did both H2O and D2O just to see if we have any difference, which of course we don't expect. So for the reaction monitoring, we choose this kind of setup where we have the reaction mixture sitting in this device. And then we just pump our reaction solution inside this kind of reaction chamber. That's a module that equipped with hollow fiber membranes, because we apply the parahydrogen through these hollow fiber membranes to avoid bubbling or foaming or something like that. And everything is sitting in a heated bath, because normally heat is, just enhancing the reaction speed. So here we used 60 degrees C for that measurements in water. Then we pump our solution through a very tiny capillary inside our benchtop NMR, where we have a widening of our capillary to an inner diameter of 1 millimeter. And then we just acquire our signal. So for that reaction of hydroxyethylacrylate in water, we see that kind of signal intensity plot over time. So this spectrum, so here you see the water peak, and here you see the FIP enhanced peaks of this protons. You see a very, very nice enhancement. And here you see the initial phase of the catalyst activation. So the catalyst have some protective groups, and they need to get hydrogenation reaction to get off. And then our real hydrogenation reaction of our substrate molecule starts. And then you can monitor just the signal intensity over time. And from that, you can calculate the conversion. So we have a 70% conversion. So the reaction was not complete. And we measured that last value in a high field magnet. And then, and with that, using only here the field points without the activation, we can just fit a pseudo first order kinetic model to our data and end up with this reaction constant. And for the measurement in D2O, the reaction constant is almost the same. As a summary, I think you see that we have, so FIP give dramatic signal enhancement, as we all know, and makes single scan spectra all also in benchtop devices very well suitable. And I think, so of course, this reaction is not the most interesting one. And for the outlook, I think we will go to heterogeneous catalyzed reactions and monitor their a new reactor type by MRI. And with that, I thank you for your attention, and I'm ready for your questions.
All right, Kerstin, thank you very much. Are there any questions? Please.
Thank you, Kerstin, for sharing this with us. For your flow-through system, if I'm not mistaken, I think the lines were relatively broad, probably due to the flow. Is that something that you're looking into?
Yeah, I would really like to do a flow compensation, because you're quite right. At that high flow rates, you get really, really bad broad lines, which you don't want to have in any spectra. And but our benchtop NMR system is not yet equipped with a gradient in the flow direction, so we can't do flow compensation at the moment.
Okay, thanks.
Great. Are there any more questions? If not, I would like to thank Kerstin again. And all the other speakers of the sessions, and enjoy your lunch.